That's a bit better. So, good morning, everybody, and welcome to today's webinar. So, my name is Richard Broad. I'm a director at the ASBP, and I'll be chairing today's event on how to choose the most appropriate lime. So, in our last session last year, we introduced our lime group, and we covered off the sort of the fundamentals of lime building products and their key benefits. So today's session is really to build on top of that. Rather than focusing on what lime is, we're looking into how to choose the right type of lime for the right application. And today's session is once again supported by our Lime Group, which is a collaborative endeavor bringing together manufacturers, suppliers, technical experts from across our membership. And the aim is to really improve understanding and share best practice for lime building products. So what you'll hear today really reflects a range of perspectives from across the industry. And there's a number of reasons why lime continues to be used across both traditional and modern construction. There's just a few key benefits listed here, but lime helps to manage moisture within the building fabric. It has a degree of flexibility. It's particularly compatible with softer building substrates. It's repairable. It can act as a sacrificial layer or material for certain types of masonry and stone, and it can support good indoor air quality. But the key point for today is that not all limes are the same. So a different type of lime behaves differently to another, and the right choice depends on a number of factors, the building substrate, sort of how exposed the building is, and how moisture is managed within the fabric. But crucially, this isn't a limitation. It's sort of one of the reasons why lime is such a versatile material. But as with any other construction approach, it does mean that selecting the right product is key. So I'll shortly hand over to Adam Brown from Cornish Lime to explain this in a bit more detail, and then we'll have some case studies and lots of time for Q&A. And for those who are less familiar with ASBP, we're a non-profit membership organisation focused on accelerating the transition to a healthy, low-carbon built environment. And we do that through events such as this, plus research, guidance, collaborating across industry, as well as seeking to influence policy. So please do consider joining a member and getting involved. And with that, I'd like to hand over to Adam Brown, who will talk us through how to choose the most appropriate lime for your building project. So over to you, Adam.
Hopefully everyone's got the screen. Yeah, good morning, everyone. So today it's more of a general overview. So we will go in and discuss sort of different lime types, strengths and considerations, also some things to look out for. So yeah, what we'll try and cover off is understanding of lime types in the market, key considerations when specifying lime. We'll also look at some of the standards and data, and then there is a time for case studies and Q&A with the wider group after. When it comes to types of lime, so the British standard, or BSEN 459, that is building lime, which provides us definitions, classifications, and chemical and physical characteristics. Now, there are two main criteria. So we have non-hydraulic lime, which is a lime that combines with carbon dioxide present in the air, and then we have hydraulic lime. Hydraulic lime is a lime that has properties of setting and hardening when mixed with water. It also does undertake some reaction with carbon dioxide as well. Now, non-hydraulic limes specifically, they can be divided into two subcategories. So we have calcium lime and dolomitic lime. Now, in our industry, these are often better known as air limes, putty limes, quick lime, hydrate, but there are a range of other options beyond these. It's just we tend to see these used predominantly. To give you some examples, so these are non-hydraulic lime mortars that are available from members within the group. These are your typical types of finishes. So on the left-hand side, you've got a lime putty. On the right-hand side is just a lime putty plaster. We then have lime with hydraulic properties. So as I said, these are limes that set with the presence of water. And these can be divided into three subcategories. So we have natural hydraulic lime, or NHL. We then have formulated lime and hydraulic lime. Now, the most popular or the most common in the UK are going to be natural hydraulic limes, and these come in three strengths: NHL2, NHL 3.5, and NHL 5. Now, interestingly, you'll see there we have HL, or hydraulic lime. So these are limes that are essentially man-made to give you very specific performance characteristics. Now, under the 459 standard, the additives basically have to be declared. So these are not natural. What we tend to use predominantly are natural hydraulic limes. And again, just a selection of NHL. So these are powders, and they're also available as ready mixed products. And we also find a range of insulating plasters and renders are available too. So to break it down further, there are probably three main types of lime that we see used in the construction industry. The first one is often referred to as hot mix. Hot mix is just a name. A hot mix is essentially a mortar, a render, a plaster, which is made from a quicklime, and you add water and an aggregate, typically sand. Now, unlike a putty, these use the quicklime as a raw material. So they're often mixed on site or pre-batched. They don't have to be hot, but when you mix quicklime with water, you start to get this exothermic reaction. You start to produce heat. That is often where the name hot mix comes from, but they can be used hot, they can be used cold. Now, in terms of some of their strengths, hot mix mortars are generally softer, so they work very well on soft and friable masonry, so they can be more compatible with sort of older historic masonry units. They will give you very high vapor permeability. They have this ability to wick moisture from the walls, reducing potential, moisture-related issues. They're very effective in sheltered and low exposed conditions, and they're very good for mass wall construction. Bedding and pointing becomes very, very easy. These materials can be quite sticky. They're very easy to build with, often much faster than some of the alternatives. They do give historic continuity, so they do align with historic methods, and you can blend quicklime with things like pozzolans, NHLs to try and mimic the performance of historical mortars that we found used in the construction. And that also gives us a very flexible approach. So we can mix and match these materials, we can blend them. Another thing to consider is these materials do tend to have quite a high absorbency level. So they will pull in high amounts of water. Now that can be also an advantage because it can help dry the masonry. But if you're using these materials in very sort of high exposure areas, subject to wind-driven rains, it is something to watch out for. Because these materials set through carbonation, which I will explain later in the presentation, they can be quite slow to develop their strength. So you do need to be careful when using them in the early stages. Relatively easy to overcome. It just needs good protection, good site management. But you do need to be careful the time of year. As temperature drops, this carbonation process can become slower, and these materials are potentially more risk, higher risk of frost damage. They do require aftercare. So again, because it's a slow carbonation process, you do need to ensure that these materials are cared for, protected. And as I said, that absorbency can be an issue depending on where you're using it. Also, some considerations. So a lot of people will state that quicklime is, a historic method of mixing. It is, but the lime that we had historically is very different to the lime today. So you do need to watch out for that. It's not always going to be a like for like, but you can blend it with materials to make it like for like. And with all of these binders, they're not all a universal solution. Each one has its place within the industry. We then have lime putty or putty mortars. So still made using a quicklime, but it's mixed with an excess of water, and then that mixture is then sat and stored for a number of months, and it crystallizes and turns into a putty. We then mix this with an aggregate to create a mortar, a render, or a plaster. Now, a lot of the strengths and considerations are going to be very similar to what we've just gone through. So again, putty mortars tend to be quite soft, so much better suited for softer historical masonry units. They offer a high permeability, very good in sheltered conditions. Where putty tends to differ is it gives very good plasticity. So it's very good for finishing work. So a lot of plasters are often made with lime putty because you can get a better finish. And again, was used historically, provides a flexible approach. As you can see, a lot of these considerations are what we've just discussed, so they are slow to gain strength. You do need to protect them during their sort of infancy. Now, the way a quicklime mortar, a hot mix, or a lime putty works is through this lime cycle. So we start with our limestone. This is generally a very pure limestone. This is then burnt. All the CO2 that's contained within that stone is driven off, and then we have quicklime. Now, quicklime is extremely reactive. Once you start to add water to it, it will start to hydrate or slake. Now, to make a putty, we'll basically mix it with an excess of water and then store that, and then that can be added to sand, or we can just take the quicklime and mix that with sand straight away. Both materials are going to give you a mortar which relies on releasing that water that was used during the mixing process and then reabsorbing that CO2 that was driven off at the early stages. So this is referred to as carbonation. This is basically reabsorbing the CO2. This is why it can be quite a slow set. We then have natural hydraulic lime, or NHLs. So these are, again, made from limestone, but these limestones tend to have impurities such as clay that give it these hydraulic properties when it's fired. So it sets through a chemical reaction with water, and it also reabsorbs some CO2. Process is still similar to quicklime. They're still burnt, but they're then slaked with a very controlled water addition in factories to produce a dry powdered material. Now, in terms of some of the strengths for NHLs, so we have three classified strengths, so we can use them for a variety of applications. NHLs, because they have this chemical set, they tend to be slightly quicker, so you can find that working times might be improved. Also, as they're stronger, they tend to work better in exposed conditions, so they're not as absorbent, and they're very good if you're in continuously damp environments. Because they set with the addition of water, they will set underwater. So if you have a very damp environment, if you're below ground, for example, these materials will work much better. Whereas, say, our hot mix and our lime putty, if water's present, they're not going to set. They also give you a guaranteed minimum strength. So your NHL classifications, they're tested, they're certified, they will give you a minimum strength at 28 days. But as such, they can give you higher compressive, or they will give you higher compressive strengths than a hot mix or a lime putty mortar. So selection becomes very important depending on the type of building you're working with. You can also find that because NHLs are manufactured in different countries, different locations, you will get variation from manufacturer to manufacturer. That's not necessarily a negative, it's just something to bear in mind. They're not all going to be the same. They also offer a lower absorbency, which can be a positive or a negative depending on where you're using it. So they might not have the same ability to wick moisture from the walls, but if you're using them in a high exposure environment, they can work much better because they're going to take in the same level of liquid water. In terms of how these materials set, as I said, we start with our limestone that contains impurities. We then burn that limestone, and then we get reactions of silica, which are contained within that limestone, so it produces reactive silicates. We're then left with our quicklime. That is then hydrated. So we mix that with a very controlled amount of water, and then that produces a fine powder, which is our natural hydraulic lime. We take that lime, we mix it with our aggregate. That material is placed into the wall. Our hydraulic set starts to take place. The water used during the mixing is driven off. Then once that hydraulic set has occurred, we get some reabsorption of CO2. So hopefully that's a very brief overview. What I'm going to try and go through now is more around the classification and designations of these materials. So if we start with air limes, so EN 459 designates air limes and it gives us a CL number. Now that CL number refers to the amount of available lime that is present within that material. So CL90, which is what we tend to use predominantly in the UK, that is the purest, it's the whitest, and it is the most reactive. It tends to have the highest amount of calcium hydroxide present. So the issue we find in the UK is British limestone sources are fairly limited. So historically, mortars would have been made using what was readily available nearby. So they wouldn't have been this sort of pure lime that we find today. Modern materials are very pure. The construction industry, we are somewhat of a niche within terms of lime uses. It's used much more in sort of processing industrial use. So CL90 being very pure, it meets the requirements of EN459 with very little processing. But we also do have CL70, CL80 available. It can be imported. but what we tend to use here is CL90. Now, also under the standard, it gives us a minimum strength at 28 days. And as you can probably work out, 0.9, 0.8, 0.7 refers to the CL number. Quick lime, lime putty, hydrated lime, they are all chemically very similar. They're all derived from the same base material. Some are just more processed than others. So, for example, you can make a lime putty from a quick lime or a hydrate. All you have to do is mix it with an excess of water, flake it, and store it. However, from our sort of findings, we always find that quicklime produces a much higher quality putty as it produces finer sort of plate-like crystals. These crystals tend to slide over each other more. So this gives us very, very good plasticity, gives us smoothness, gives us much better cohesion within the mortar. Whereas a hydrate tends to be a coarser crystal that doesn't behave as well. Also, for anyone that's interested in making their own putty, what we generally find is hydrate is often picked up from your builders merchants, may have been stored there for quite some time. It may have already started to carbonate, so you don't get the same reaction. We then move on to NHLs. Now, there is somewhat of a growing trend in the industry where a lot of people are saying NHLs are too strong and they get stronger over time. Now, technically, they do get stronger over time, but are they too strong? This is one that's up for debate. Again, under the standards, we have a minimum strength that we have to achieve at 28 days. So NHL2, for example, that has to achieve a strength of 2 newtons at 28 days. It doesn't give us our final strength. That is our 28-day strength, as then 3.5 and then 5. Now, this distribution bell curves, it indicates the range of compressive strengths that may be available. One of the biggest issues within the standard, or 459, is that it's done in such a way that ensures replication. So under the standard, the materials are mixed at a 1-to-1 ratio, so 1 lime to 1 sand. This is far stronger than we'd ever use them on site. We also use an engineered sand that's graded to have the best particle distribution. That creates a much denser material that requires less water. So that in turn increases the strength. So the standard isn't actually replicating what we would use on site. So it is very important to sort of bear that in mind. Now, when it comes to binder chemistry, this is where the materials tend to differ. So we have our CL90, that is going to be 90% plus available lime. If we compare that to an NHL, depending on the strength, that's going to be anywhere from 15 to 55% available lime. We then have baelite. Now, baelite is the reactive component in an NHL. When we add water to it, it starts to set. So in a CL90, that's going to be less than 5%. In an NHL, it could be anywhere as high as 30 to 80%. But NHLs will vary depending on their source rock. So when we're comparing brands, they are going to behave slightly differently. Again, it is a minimum strength that we have to achieve. So NHLs, they're not produced in the UK. Our geology doesn't really suit it for commercial scale. But again, it's important to know these are minimums. These standards weren't designed as a specification standard. They're designed as a manufacturing standard. And unfortunately, I think that's where a lot of the stigma around NHL comes from. It's often quite misunderstood. So it becomes important in looking at the specific brands, looking at sort of longer term strength data, and just knowing what you're selecting. So again, in terms of the available free lime, under the standards, NHL2 has to have 25%, NHL 3.5 is 15%, NHL 5 is 10%. Again, these are minimums. Now, this is data that we've taken ourselves, so they're on our own materials. I'm sure other people in the group will have their own data, but it's looking at long-term strength development and long-term performance of these mortars. So what we need to focus on is the brand. That's not saying one brand is correct, one brand's incorrect. All these brands work, but just ensuring you knowing what you're getting at the end of the day. So as a comparison, you can see we've got a quick lime mortar, we've got a lime putty mortar, we've then got an NHL2 and NHL 3.5. You'll notice so this is based on a year's worth of testing. So we know that the NHLs have reached their final strength. So you can see compressive strength, quick lime, lime putty, NHL2 in this particular brand, they're all around a very similar strength. We then start to jump up. Once we go to the NHL 3.5, we do start to get stronger. You'll also see quick lime and lime putty, they have a better flexural strength. But where they start to change is around this capillary water absorption. So quicklime, lime putty, they're going to take in more water. And we start to see as we get stronger, that absorbency reduces. Vapor permeability. Quicklime, lime putty tend to be much more vapor permeable. We then start to see this increase as we get stronger as we go on. Now, all limes have their place, and ultimately what we're trying to do is manage moisture within the construction. Moisture, it's always been a threat to building, and it always will be a threat. Now, lime has protected buildings for centuries, so it's important, we still continue to use these materials. We just need to ensure we're selecting the right one. Very often, what we will look for, especially with external applications, is location. Location becomes fairly critical in our opinion. So this map is based on the BRE rain indices. These figures are slightly outdated. They're based on 1981 to 2010 averages, but it just maps the UK in relation to exposure to wind-driven rains. So you'll start to see, we start with sheltered locations. Now, a sheltered location means that for every rain spell, there will be 33 litres of wind-driven rain per metre squared or lower. We then move into moderate exposure. We go up to 56.5 litres. We then move to severe exposure, which is up to 100 litres. And then finally, we have very severe. Now, this means that for every rain spell, there will be more than 100 litres of wind-driven rain per metre squared. That is a huge amount of water which is subject to the masonry. So the materials we use externally in these environments are going to potentially differ to those that we use in a sheltered location. To give you an example, Cornwall, where we're based, is one of the wettest counties in the UK. It rains for about 146 days of the year, so about 40% of the time. So whenever we're doing sort of technical work, a material we use in Cornwall might be very different to that we'd use in London, just based on the exposure that we find ourselves in. So when it comes to managing moisture, there's lots of different terms available. We tend to work on three key criteria. The first one is permeability or vapor permeability. That is the ability of the mortar, the render, the plaster to allow moisture to pass through it. We then have capillarity. That is the ability of the material to release water or liquid. And then finally, we have moisture buffering. That is the ability to actually pull in and release moisture. So we do need to work for all three. Now, when it comes to selecting appropriate materials, the first thing we'll always try and do is go for as higher permeability as possible. We want moisture to be able to transfer through that material with relative ease. Capillarity, as I've just mentioned, that's going to depend on where we're doing it, depending on exposure. Moisture buffering becomes a little bit more complex. It often involves insulation. It can be measured, but that is something to consider as well. But ultimately, what we're trying to do is prevent this issue of decay. Moisture is always present. So we're dealing with masonry units that have some level of porosity. We have no cavity present. Moisture is always going to be there. Now, the mortar joint within that wall is critical in how we manage moisture. The mortar should always be softer than the host masonry. So this allows for moisture to move through the mortar rather than, say, the masonry unit itself. So the performance of that mortar becomes critical, as then does any sort of render or plaster or paint that we put over the top. But it has to work both ways. Very often we see a lack of moisture movement, and then we get issues. Also, we are now starting to see an issue with too much movement and buildings becoming saturated. So material selection becomes very, very important. Now, looking at modern mortars compared to, so cement mortar compared to limes, always done here. So this is on the left-hand side, you've got a cement mortar. On the middle, you've got a lime putty. On the right-hand side, you've got an NHL 3.5. This has just been injected with a blue resin and then put under a microscope. You'll notice the blue connected structure. So the more connected that structure, the more moisture is going to be able to move through it. It's the material's pore structure. Think of it like arteries. The more connected the structure, the more moisture is able to move through there. Now, there is some connection still on the sand and cement mortar. However, because cement is so much stronger and so much denser, that structure is significantly decreased. Moisture will always take the path of least resistance. It's always going to try and escape. Now, what lime does is allow for that moisture movement to occur. So this is an NHL 3.5 mortar. This building is extremely coastal. It basically sits on the edge of a pier. You'll notice there that the mortar is starting to degrade. So what we're actually seeing is moisture being moved through that mortar joint, And unfortunately, because of where it is, it's taking salt with it as well. That salt is then sort of crystallizing near the surface and damaging the mortar. But you'll notice that the brick and the stone around it is fully protected. This is often why limes are referred to as sacrificial. It's much easier to replace the pointing in this instance than it is to replace the brick or the stone. Whereas we flip that to a sand and cement mortar, unfortunately, we have the opposite occurring. Moisture or water is present, it's trying to escape. That cement doesn't have that connected pore structure. It will take the next or the easiest path of, or the path of least resistance, which unfortunately then ends up being the masonry unit. We get this gradual erosion over time. I'm sure if you drive through any town or village in the UK, you'll see where, for example, on an old stone building, cement mortar stands proud. The joints look like they're sort of proud of the stone. Very often, that is just a sign that moisture is present and is basically eroding that stone over time. We also can get issues with cement renders, cement plasters on older backgrounds. Older buildings, they are prone to movement. They will expand and contract as they get wet, as they dry out, as they heat and they cool. So it's very important that the materials we use have this ability to move with it. Cement render expands and contracts at a very different rate to the masonry background. So what you're seeing here is basically the cement render has a much stronger bond to the background. It pull the weaker substrate apart as it moves. Eventually, you get this separation or delamination over time. On the left-hand side, we've got a gypsum plaster. Now, this has got wet. Gypsum is essentially a salt. That salt has then basically transferred through and then back out again. It's recrystallized near the surface, and we get this expansion and failure. On the right-hand side, so this is lath and plaster. Unfortunately, again, water has just got in. Lath has gotten wet. That's expanded. The mortar was just too strong and hasn't been able to deal with that expansion and blown. So when it comes to lime, there are also factors that affect lime's performance. Lime isn't some magic cure. We still need to understand what we're using and how we use it. So seasonality can be very important. What we're looking at here, this was a building that we supplied. It was a lime putty that was carried out in October. Now, unfortunately, it was too cold. We then had freezing temperatures. Water was present. That water froze. When water freezes, it expands by about 7%. And all you're looking at is that the surface was basically too weak. Here, we're looking at lime bleed. So this is very likely that lime hadn't converted sufficiently, it hadn't undertaken carbonation. It got very, very wet. And this excess lime had basically washed out over the surface. On the left-hand side, this is a sign of efflorescence. So this is actually a modern cavity construction that had been faced with a granite. It's a bit of an unusual one in that it had a DPC behind it. Now, that granite was actually a very, very porous granite. Water was being pulled in and then basically dropping behind. And as it was coming back out, a lot of salts were being carried through with it. So again, lime is still subject to potential issues, but we can mitigate those with good protection in most instances. So when it comes to specification, we have 6 sort of key areas that we'll always focus on, or criteria. So the first one is compatibility. So we always want to ensure that we have a lower compressive strength than the masonry unit. The second one is elasticity. These buildings undertake movement. We need to ensure that the materials we use are going to be able to move with it. We'll then look at vapor permeability and capillarity. Again, we always want to have as high a vapor permeability as possible. Capillarity, that's going to depend on where we're using it, internal, external location. Bond strength, it needs to sufficiently bond. We don't want it to be too strong. We don't want it to be too weak. Workability, it's often one that can be missed. But again, if you create the most sort of technically sound mortar or render or plaster, if it's not nice to apply, people just aren't going to use it. And then finally, reversibility. It's not always going to be the case, but ideally, we want to be using materials and doing work that we can actually take back out or remove without causing any damage. Now, lime is also frequently used on modern buildings. It isn't just material that is used on sort of solid wall historic buildings. Modern buildings, they still do have moisture risks. I mean, cavities are designed to try and deal with that. But some of the risks that we often come across with a lot of modern materials, you have a closed surface or a capillary block. That forces water to run down the surface. One issue you can find is you have incorrect detailing. If you have cracking, that runoff can actually funnel water back into those cracks. can become an issue. Also, with capillary blocks, you're very often relying on chemical additions. These can break down on weather over time. You then can get moisture transferring through the wall due to poor insulation, due to wall ties. Saturation and settlement in the cavity can cause thermal and cold bridging. So moisture still can work its way into a modern building even when a cavity is present. Also, a lot of people just like the aesthetics of lime. It looks nice. It gives you the sort of benefits that we get within historic buildings. We still can have that in older buildings. We still can manage moisture. We can reduce condensation. We can reduce mold risk. So it can be better for the occupant. It can be better for the structure. It provides good flexibility. We have high alkalinity. We're not often using synthetic additives. VOCs tend to be much lower. We're not using high additions of chemicals. Also, it can provide a really nice aesthetic finish. It gives you a nice soft texture. You can change the textures with lime-based materials by adjusting the aggregates. So you can get a really nice finish even in a modern context. Now, in terms of practicalities, so handling the material, applying it, and curing it also have a significant impact on how that material performs. So one of the most important things we need to look for, we've chosen what lime we're going to use. We now need to look at the type of aggregate that we use. So this is actually critical in how that mortar behaves. So it also will influence the compressive strength, dimensional stability, and provide adhesion and flexibility. Using the wrong aggregate can actually cause some significant issues. So for example, sharper or coarser aggregates, they can help aid carbonation. So they allow for better moisture and CO2 absorption. It's very important to use clean aggregates. Again, this can depend on where you are. For example, here in Cornwall, we have really sort of unclean, like clay-based aggregates that can cause issues. Also, we have a lot of salt in our aggregates, so we often have to wash them or import them. Salts, as we've been through, they can crystallize, they can damage the mortar itself. Clays, they'll increase the water requirement. As we add more water, we potentially increase the risk of shrinkage. Fine and dusty aggregates, they can block the pore structure. That can reduce carbonation. So again, clean, well-graded is really what we're looking for. Clean, well-graded aggregates. Now, the application will also determine the best type of aggregate to use. So for example, if we're looking at rendering and plastering, any sort of base coat work where we're building out at depth, 10, 15 mil, a washed coarse material is going to work much better because it allows us to apply it that much thicker. Whereas if we're doing finishing coats, a washed finer material is going to allow for that thinner application to be used. So 6 key areas that we try and focus on when using limes. So the first one is season. So when specifying materials, we need to be aware of the weather, how that can impact the material, carbonation, strength development. Lime putty, quicklime, they're brilliant, highly vapor permeable binders. They make brilliant mortars. However, they don't have a chemical set. So we need to be careful. We need to ensure that it's not going to be a continually damp, wet or cold environment. Weather. So again, environmental conditions. Often people will look for rain and sun. That can cause issues. Also, wind is a very sort of important thing to look out for because you can get wind drying. We can overcome a lot of these issues with just good protection. So Hessian is a wonderful material. It can protect the fresh application. So it can help keep the material damp. It can also be used during winter to protect it from sort of frost and cold. We then need to look for a water addition. If we're site mixing, this becomes very important because if we add too much water, we're potentially going to increase the risk of shrinkage. We may cause lime bleed. There are now, I'm sure everyone in this group supplies pre-mixed materials that do take a lot of this risk away. The other thing we need to then focus on is suction from the background. Background suction will influence how that material behaves. So absorbent surfaces, such as dry masonry, that will pull water out of the mortar or the render very, very quickly. So again, we need to ensure that it's sufficiently dampened so we can control moisture within the background. Then finally, curing. So all of these materials will take some form of carbonation is going to take place, and that can be a long process. So we need to ensure that it's protected during the initial sort of application or aftercare, and that the material is able to cure sufficiently. So that was a very general overview. Hopefully that covered a lot of ground. But I suppose the key takeaways for today, not all limes are the same. Understanding the differences is essential, but they all have their place. The right choice depends on context. So it's going to depend on the substrate, the exposure, moisture, background type. There's a lot of factors that we need to take into consideration. but compatibility is key. Strength, flexibility, and permeability should always suit the building fabric. Every building is going to be slightly different. Good performance relies on good practice, detail, application, and curing. These are all critical. The materials are still relatively easy to use. A lot of people will come to us and say, I've never used lime, I don't want to touch it. They think it's some sort of dark art in applying it. But any plasterer can apply lime, anyone can apply lime. It's just ensuring, knowing sort of the aftercare process to ensure that you get a good sort of finish and material sets correctly. And lime has a vital role in both conservation and new build. Finally, there is help on hand. So all of the members of this group, we all have sort of technical experts involved. All of us will be, more than happy to help with any questions, any application advice. Just reach out to us. And thank you for listening. I need to end my share. There we go.
Excellent. Thank you so much, Adam. That was a fantastic overview of all the different lime types. There's a couple of questions coming in, but I think we'll save them for the Q&A later. So please do keep adding your questions to the Q&A and we can sort of get into the detail a bit more later. Okay, so next up we've got a couple of case studies. So if I could ask John and Nigel to present first, that would be fantastic.
Morning, everybody. Thank you very much for that presentation, which was great. It's really hard to get all that information in. But that was a really good presentation, Adam. Trying to get ours up now.
Get some technical help.
Have you got two screens? We're seeing a nice hill at the moment, which looks like a nice place.
It's lovely, isn't it? It's not Wales. Not sure where it is. Sorry, the presentation's buried here.
We'll bear with you, no problem.
Lovely.
Excellent.
Yeah, so this is it's a bit of a last minute, as a lot of these things are. Look at a case study which we've been conducting, and one of the things we were often debating is the importance of skills, which obviously there's a great lack. So skills detailing the materials, and out of those, in some ways, the material selection is the least important, because if you don't get the other stuff right, then your materials aren't going to work.
I don't know how this works.
Oh, I'm very sorry. There we go. Yeah. Right. Okay. So this is a project which we took on to look at various aspects of building. So it's a listed building. It's in a conservation area. It's got bats. It's got structural issues. It's a hard to treat building. So it's a case study which is looking at pre and post insulation monitoring, seeing performance of moisture and temperature running through buildings. It's got the added problem of or interest of it's actually a jail, former jail. 1842, which is the far section of the building, which was the cells below, governor's house above, and then this extension, which is protruding here, which was built in sort of 1870 when they needed to provide more space for miscreants of Brecon. There were 4 cells in here, so looking at how buildings fall apart, usually it's not just one issue that's caused the problem. It's a number of issues, and sort of trying to investigate that is obviously an interesting process. So there were division walls in here. So this line that runs down here, you can just see the shadowing of brickwork. There's another line here and here. So these were the division walls of each cell. So there were 4 cells running down here, and there was another one on this side of the building. Come 1890, they built another jail, so they didn't need this to be cells anymore. So they removed these division walls, which then weakened the wall a little bit. Along this side of the wall here, they then put a channel in because there were fire engines kept in here. There was lots of washing water running around that needed to be dealt with, so they ran that down into the ground. Unfortunately, the gully that ran into then was broken, so it caused a bit of damage here. And these are then heating pipes which were linked into a boiler that was stored down in the basement. This door here was originally a window, but when they converted it into a fire station, they extended that into a door, and they didn't do it particularly well. So you can see this sort of separation of these skins happening on both sides. So there was just general movement that had happened that had been exacerbated by potentially a bit of ground movement as well. So it's built on a really awkward site. So this is a, a considerable angle coming down here. So we needed to provide some terracing to give it some support. And that was done with reasonably heavy-hand engineering solution, but to satisfy various people, it had to be done in a way which would support the building. And decided to use a hot mix here. So there's a very sort of characteristic, as Adam was saying, in Cornwall, where you have soils, and this is found in most mortars, where you've got uh, virtually as dug materials used as your aggregate, and the soils give it a particular colour, and trying to replicate that and make a workable mortar is quite challenging. But anyway, this was produced with a combination of a well-graded sand and also an element of subsoil, and this was then mixed with it was actually a kibble lime mixed on site, which reduces the sort of dust element of it considerably. And it's trying to be sort of more faithful to the original mortar. It was mixed in a barren mixer like this, mixed to sort of fairly dry consistency and emptied out and then stored. So we supply all these as dry hot mixers as well. The Also we used a bell mixer and just appropriate mixing methodology of when and how you put those materials in churned out a very simple and considerable quantities of material really to build that whole wall. We needed to match the build quality of the original wall. So the whole of that back wall, as you'll see, that all came down and was rebuilt. There was a certain amount of protection around the whole thing because it was scaffolded. So actually, protection on there was fairly minimal. We're very lucky with the weather as well, and the knowledge and understanding of the builders on site. They knew what and when to protect those elements. So that familiarity is just absolutely crucial. And this work happened between January and April. And because it was a build as opposed to a repoint, you got even more time, obviously, to finish these things because there's a greater mass of mortar and moisture, which dries off much more slowly. So you've got much more time to do that brushing back and tending and finishing. Generally churn brush, and there have been some situations where used a wire brush on it just to get off the to tend it back so it looks very similar, and it is still workable 3 weeks later. This is being built. It was built up and then pointed just to bring it off flush. You can see that this is obviously still quite damp, but the colour is going to blend in and be very simple. It's sort of fairly identical to the original mortar, and that's what it looks like on the inside. So as a lot of the group would have very similar situations where you're working with or being asked to help with a specification going into the winter and working through the winter, and we have to be quite cautious because you have to have utter confidence in the builders. So this is just a nice demonstration of what you would be cautious about suggesting to people, but we've used the softest of all the mortars, and I think this is probably going to help the building. But just demonstrating that it's possible to do that with good knowledge. So generally, we would have gone towards a 2 or 3.5, I guess, to build that. Making sure that adequate protection is provided. The skills and knowledge are absolutely critical. As I say, I think they're more important than the materials you can use. If you have a very good builder, they can use pretty much any material to build to a degree. But the detailing of the skill of the build and the detailing of the build is absolutely crucial. So I think that's it.
Excellent. Thank you, Nigel. Really
Yeah.
interesting case study showing the sort of versatility of lime products. So I think we've got some more case studies now from Dominic, which I will share screen. If you just bear. Okay, hopefully you can see that. Are you ready, Dominic?
Yes, I am indeed. Thank you.
Excellent. Right. Away you go.
So, hello everyone. Thank you all for joining us today. I would just like to briefly take you. My name's Dominic Putnam. I look after marketing and business development at Lime Green Products. And quite a few years back, we developed a wood fiber based wall insulation system, which we now have. In the case of the internal system, is a fully accredited Kiwa system. And today I just want to share a couple of examples of projects that we have supported in the last handful of years, starting off with a new build construction and then moving on to a retrofit example in London. So first of all, we start here with Cannock Mill, which is if you want to just move the slide, Richard, that would be great. Cannock Mill was a award-winning co-housing project near Colchester in Essex, which comprised 6 apartments and 17 houses. Every home is built to meet Passive House standards. The whole concept behind it was to create affordable, healthy, sustainable homes, which was key for the architects, and Thorne Architects, who are based in London, did all the design work. And to quote the founder of that business, they wanted to create a natural, energy efficient, and most importantly, healthy homes. So they put a lot of work into sourcing breathable materials for the building's fabric to ensure the homes would be healthy for both their occupants and the environment. So right materials, product system selection was very important. The work started in spring 2017 and was completed autumn 2019. So to achieve a healthy build, which was timber frame walls were chosen with Lime Green's external warm shell insulation system over the timber frame studs. And this system consists of wood fiber insulation boards rendered with Lime Green's base and top coats, prep bond finish, lime render products. So very important to this project, as with many, obviously, is how to achieve important energy savings. We know from follow-up discussions with the developer and current residents that their average fuel bill for the properties is estimated to cost the equivalent of a cup of coffee per fortnight. Warm shell system promotes breathability and delivers excellent heat control. So this has resulted in extremely low Passive House compliant U values for each of the buildings, making the homes very economic to run. It was also important that this, because it was a private residential development, that the architect was very particular about involving the community. So effectively her clients were a group of residents who wanted to set up a community living. And so they chose between them our coloured renders, which had been previously used on a school in Romford, for which the result had been recognised. And so they involved the future occupants in the design from a very early stage through various workshop sessions, and they settled on these choice of colours: ironstone, ochre, Corfton, and terracotta. So that's where you see that sort of almost rainbow effect on the buildings, which makes the whole area attractive. If you could move. Yeah, so here you're just seeing a few quick shots of the development and the area, which was built around a mill, a traditional mill house. And then finally, in conclusion, so clearly a very important factor, the price, the cost of this construction and the systems that were selected were, important. And even though it did cost a little bit more to build passive house standard construction versus current building regulation minimums, the resulting low fuel bills and healthy environment will, in the longer term, have already more than made up for the additional cost. And we're pleased to show here that 7 years in from when the development was completed, the whole site is maturing well and the render looks great. So moving on to our second case study. This is a retrofit solution at a property in Chelsea in Kensington, London. The project really was to address what they were going to do with this existing asset, and there was initially a plan to demolish, but they then had to accept that it could not be demolished because of the nature of the building, and so they agreed on bringing the Edwardian buildings up to modern living standards, which was going to deal with 4 blocks that were at that point in time uninhabitable. So a big project started off as 159 dwellings across the 4 buildings, with a range of sort of bed sits and right through to bigger apartments. So they've been completely reconfigured, and the buildings now comprise 81 1 to 4 bedroom properties. And obviously with the modernization of the facilities, they included lifts and balconies in order to make the homes more accessible and bright and airy. So again, choice of materials was very important. It was critical for the housing developer, who's in fact a company who many of you will know is Clarion Homes, for them to keep this solid wall homes warm and damp free. And our internal warm shell accredited system was recommended by the specialist moisture consultants who were involved with the project right at the outset. A clay system was considered, but 2 key benefits with warm shell were that it takes up much less space within the apartment areas than a clay-based system, and is also less costly than the clay system. So in this particular case, the depth of wood fiber product that was adopted to achieve the desired U rating was only 40 millimeters, and this provided them a 60% improvement in their energy costs. So just to wrap up, summarizing, the warm shell benefits provided a great improvement to existing building in terms of U value and air tightness with the least incursion. And given the reconfiguration of the spaces that I mentioned earlier, the new apartments are really spacious. So as is probably not uncommon, in the initial discussions with Clarion Homes, they wanted to know why, they really wanted just to crack on and do things the way they'd always done them. Why would they need to adopt this sort of wood fibre system? Could they not just do a steel frame system as they've done in the past? However, obviously, to comply with the government's best practice guide, building regulations, BS 5250, moisture in buildings, the simple answer is no. So to avoid condensation problems, if you form a void cavity on the cold side of the insulation, which a stud or metal frame system does, then this void should be ventilated to the outside to ensure no damp or mold growth occurs. In turn, this would mean that the stud wall should be protected from drafts from the newly ventilated space using a wind-tight breather membrane. And then on the room inside, you can insulate between and over the studs to cut thermal bridging. So that this was their challenge. Sounds straightforward, but in practice is almost impossible to do. So essentially, they're converting an old building to work and perform like a modern cavity wall is much harder in flats where the cavity cannot be continuous across the whole wall or neighbouring flats for fire safety reasons, and almost impossible around windows to achieve this. So very important to them at this point was to think about the building and do the right thing for the building, making sure that for the future it could breathe, maintain its integrity for another 100 years. And one way to keep the costs low on projects like this is to use wood fibre insulation, which, as we're dealing with today, takes a direct application of lime plaster. So this is where it's needed as a wood fibre, and was exactly what was done here. So it was only needed to be installed, as you would expect, on the external facing wall areas. So the internal walls within the apartments and communal areas were upgraded with traditional plasterboard systems. So just to summarize, in terms of this particular study, you get the best of both worlds with warm shell or an equivalent wood fibre insulation system. The system is proven to protect the integrity of the solid wall building, allowing it to breathe while substantially improving the thermal performance of the building. And fitting the system is really straightforward. There was limited use of base materials to level out the walls prior to board insulation, as the buildings were incredibly plumb. And it's a real testament to the quality of how we used to build 100 years ago. So Sutton Dwellings is, in summary, a great example of how period building can be reimagined with so much old housing stock around the country lying empty because it doesn't feel there is a viable way to bring it back into use. Systems such as warm shell or equivalent wood fibre solutions really do provide an opportunity. Thank you. And if anybody has any questions, I'll be happy to try and field those.
Excellent. Thank you, Dominic. So yeah, I hope that was useful. That was just a few case studies to show the sort of versatility of lime products and the different applications, for conservation and new build to, passive house standards, and also how they can work alongside complementary products like wood fiber insulation. So good. We've got a number of questions coming through. So just a note to say, if there's any of our Lime group members in the other side watching in and they would like to join the panel, please raise your hand and we'll transfer you over so you don't feel left out. But we'll go to the Q&A now. So just bear with me. Right. So panelists, hopefully you can see the questions if you click on the Q&A, but I'll read it out too. So I'll start with Merlin's question. So he's saying, looking at the sort of the moisture topic, is moisture really a threat to buildings or just something we need to be aware of and work with? So he's suggesting that moisture isn't the enemy, but an important force we have to understand and respect. And if traditional buildings were completely dried out, then that might cause issues too. Any thoughts there from the panel?
I was hoping the presentation got that point across, really. Uh, I use the term threat in there because a lot of clients that we have that aren't used to construction, for example, homeowners, they see moisture as a threat. But I
Yeah.
think really what everyone in this group is trying to do is show that it isn't a threat. We just need to manage it effectively.
Mhm. Thanks, Adam. Okay, and then we do have some quite sort of specific detailed questions. So I'm just going to see if there's anything slightly more um, general. So yeah, we've got quite a from Antoinette. Antoinette, can I perhaps bring you in here and ask you to ask your question out loud, if that's okay? I'm just seeing if you're in the attendee list. If not, I'll read it out. So Antoinette suggesting she has a 1900s railway terrace for their next retrofit project. It currently has EWI with a cement render that they want to remove to restore the original brickwork. What's the best lime mortar to repoint old red brick that will complement the moisture, movement, and colour of the original brick wall? Any thoughts?
Well, judging by the presentation, that depends quite a lot on where you are in the country and
Yeah,
how soft or dense the brickwork is,
And when you're going to do
and
it.
the time of year. So,
Skills available.
yeah, it all comes down to finding a suitable contractor who understands the nature of the building and the products available, really. There are there's a wide choice of colours available, which are created by the colour of the sand or aggregate used. But generally speaking, older brick buildings, you're not going to go far wrong with a lime putty mortar or a hot mix lime mortar, as long as appropriate protection is used later in the year or any time of year, to be honest.
thanks, John. Yes, I was hoping Antoinette could come in to give a bit more detail, but I think she's had to drop off. So not to worry. We'll move on to another question. So this one's a bit more of a broader point. So somebody's asking when breathability is mentioned. I know there's a bit of a discussion about that word generally, but yeah, what do we mean by breathability and how is it measured?
It's a meaningless term in my opinion. So when we're looking at moisture movement. So what we'd always focus on is vapor permeability and capillarity. Yeah, I think the term breathable is it's used. We all use it. I use it extensively, but it's a bit of a cover-all that can be used for lots of different things. But really, what we're looking at is moisture movement and water movement. So it's capillarity and vapor permeability is what I would probably recommend they focus on in terms of how moisture and water moves through a material. But it's just easy to say breathable because most people understand it in that way.
Yeah, understood. Okay. Yeah, please keep adding your questions to the chat. I'll just work through them. So, um, this is a question I think for Adam about one of your photos. So it says for the granite that effloresced, did the DPC behind it play a role in that?
Yeah, I probably didn't explain that one very well. Sorry. So it was a modern construction. The granite was extremely porous, but the DPC was layered behind the granite. So what had happened is excess water had got into the wall, but it wasn't able to drop into the cavity. It was a design issue. So basically, that was just being cycled back out. But as it had got very wet after the pointing had taken place, you're basically just recycling that lime back through the wall. So yeah, the lime hadn't cured or set sufficiently, so you were just getting this excess lime bleed that was continually cycling. So the DPC was installed in the incorrect way. So the cavity was essentially meaningless in that type of construction, unfortunately.
Okay, thanks, Adam. Okay, there's another question from an anonymous attendee who says, if sharp sand is switched to building sand, so this is about aggregates for use with an NHL 3.5, stating that it should only be used with sharp sand, would you expect to see issues with curing, water retention, or the strength of the mortar?
I mean, from the presentation, yeah, and I think Nigel explained it much better in his one, it comes down to the contractor ultimately. Yeah, sharp sands are generally recommended because they are slightly better depending on what you're doing it, but it often will come down to the skill of the person using it and ensuring they're, curing it correctly.
Contractors will often like a soft building sand because it spreads more easily, because the particles are rounded, they roll over each other. So it's easier for them to use. But that rolling of the aggregate particles also means that you don't get that extra strength that you get from a sharp sand where the particles interlock. And the other factor to bear in mind is that a lot of building sands, soft sands, are fairly uniform in particle size. And you actually want to grade from the largest size right down to very fine dust so that you're not getting big voids between each particle, or relatively big voids between each particle of aggregate, which can increase it reduces the strength of the mortar or plaster, but it also excuse me can increase the risk of shrinkage as it dries.
Great, thanks, John. Thanks, Adam. Okay, a couple more questions. So this one's about working with a particular substrate, so with flint. So project with a very weathered flint wall, they need to rake out the mortar and clean it as there's algae. It's a 1600s grade 2 listed property, and they'll be repointing with 3.5 NHL lime. Any advice for the best outcome when working with flint? Obviously, we don't know the full sort of how exposed the property is, etc. But yeah, any sort of general thoughts on working with flint?
At the end of the day, flint is just another masonry unit. It's a particularly hard, dense, and impermeable one. What I would take more consideration of is the material that's forming the framework for the flint panel, which is often a much softer brick. So you need to bear that factor in mind more than the flint itself.
Okay.
And the fact that the flint is very hard means that it has less absorbency, so a lot more work is going to have to be done by the mortar in terms of releasing moisture. So it's again, it's sort of pointing towards a softer end, and with most flint walls, you do find, so based in obviously chalk areas, your base material is probably going to be from that same geology, so it's going to be a softer mortar. But it then you're sort of sticking yourself in a vulnerable situation by suggesting a softer mortar, which then requires greater tending and better weather to work with. We get a similar situation up in North Wales, where you've got a lot colder, your weather window is a lot tighter, your stone is very hard, and sort of slightly counterintuitively, you find the mortars are really, really rich and really, really soft. And I think that is to do with the fact that, but there's a great difference, isn't there, between, as I said in that case study, the rebuilding a wall is completely different to repointing it. The extra strains put on just applying a layer of pointing and the absorbency of the material around it, the rapid drying of it, it's that much harder. You've got rebuilding a wall, you've got all that mass which is holding on to a certain amount of moisture feeding off, and that sort of battery of moisture protection is that much harder. So they're distinctly different processes and strains put on the work.
Thanks, Nigel. Okay, this is a question about self-building with timber frame construction. So Kaya is keen to use lime-based mortars externally and internally. And the case study that you presented, Dominic, was particularly interesting. Perhaps you can come in here. So, any thoughts on using lime products with timber frame construction? Somebody has commented that timber frame is prone to some structural movement. So, yeah, any thoughts there, Dominic, on how best to get a good result with timber frame?
Well, I think I mean we've supplied particularly the well, it could either be an external system or sometimes the internal wood fiber lime system, and it it works very well with a timber frame structure because obviously the stud timber system is erected, and then in fact it gives people the option to have additional insulation, which could be in the form of a soft wood fiber panels, which can go in between the studs. So in our experience, this has never really presented an issue. I mean, obviously the groundwork for a timber frame extension has to be compliant with regulations, and that will determine the sort of stability of the extension unit. But certainly when it comes to application of lime external render onto wood fiber on a timber frame system, it works extremely well. Or equally, if the choice is to apply lime internally, but maybe there could be other materials used externally, might be, for example, timber cladding. There's become quite a popular contemporary design feature, which may be part of what's happening externally. And so, all these, the great thing, as has been mentioned by all the presenters, is the sort of flexibility of lime, and the fact that because we can apply, or because a lime-based internal or external lime render can be applied directly onto wood fiber boards, it makes the construction system is very simple.
Thanks, Dominic. Okay.
If I can just add,
Yeah.
as being based down in East Anglia, we have a vast number of timber frame buildings, and there's been a huge amount of research done into chalk-based plasters for that reason. So they were found historically on lots of timber frame buildings, and investigated and found to be more flexible in lots of cases and lighter weight in lots of cases than sand-based renders. So timber frame buildings, I would say, investigate a chalk-based plaster for that reason.
Excellent. Thanks, Graham. Nigel?
I don't think the problem is the material going on top of it. I think the problem is how the timber's stored. So that if the timber's moving, then it means that it hasn't been stored correctly on site because it's got moisture in it. And you often find that you go to a site and you see a load of stud work ready to go into the building and it's getting rained on. So it's inevitably going to move. So whether you use cement or whether you use lime, actually you're not going to solve the problem because the problem is in a different area. But if you then use lime on top of your system, on top of wood fiber boards, which is the system which we use as well, then you have greater flexibility, greater durability, greater resilience.
Anything to add, Adam?
I think that's covered all the
Yeah,
main points. Yeah.
Okay, I'm going to try and bring somebody else in. So, Leap has asked a question. I'm going to try. I don't know if you're still there. And is this Mark? And we'd like to ask you a question about hot lime.
Yep. Hi, Richard. Yep. Yeah, so I've been looking at different lime mortar specifications on traditional buildings and looked at the use of hot lime in terms of, because there's a lot of research by David Wiggins and people on that. But I've never quite got to the grips with how that can then be broken down in terms of appropriate mortar specifications for buildings. I was just wondering whether there's any kind of perspectives on how to develop appropriate hot lime specifications?
I think it's very hard because so much this is building by building, and is what we're all looking for is a prescribed way in which you deal with a problem, a mortar for a building type or a building region or whatever. And I think, unfortunately, that the reality is you need to gather information. You need to gather information about the building itself, its condition. You need to gather information about its exposure. Again, the skills of the people who are, are we choosing a mortar to suit the builder or the building? And we must really be looking at the building and the building's needs. But there are a lot of other factors which influence that. I mean, we do that by generally asking for a sample of mortar, which we would then do some analysis on and try and come up with a pragmatic way of solving that problem with that particular aspect of elevation or build or building and location. It's clunky and it's time consuming, but I think to be responsible in the way that you deal with it. It's a tough call, really. And everybody wants the bag from B&Q, that does the job, as we do in a lot of aspects of life. But I think it's actually about trying to identify the building's needs.
Yeah. I mean, what I've found is when we've done samples, often the response, maybe it's not, maybe we haven't quite approached the right people, kind of, but the response has always been, well, just use the NHL lime, and I think that from a moisture management point of view, certainly when we're looking at lower energy retrofits, there's a lot of positive credentials with the hot lime as a strategy, and concerns about how NHLs harden over time. Yeah.
We flog a colossal amount of hydraulic lime, and I often wonder whether that's the right thing to do. It's very hard, but you can't manage every single bit that goes out the door. But I think we're often going harder rather than we should do. That's sort of why that presentation, the case study, was looking at a building of pretty considerable size and stress that has been done just in a fat line. But I've got an incredible builder who understands what he can get away with. It's the problem we face, isn't it? Skills.
Yeah.
Thank you both. I think it'd be interesting to explore the skills question a bit more. We've said that if you know what you're doing, lime products are very easy to use, but are there enough people who do know what they're doing? And if not, how can we change that?
Um, we've got an industry that struggles to use sand and cement largely. To be honest, it's an education issue. I know locally for us in Cornwall, there's no skills-based training available at colleges. It's something that we've tried to push back in, but I don't know. Without getting too controversial, it's new build, slap up, build as much as we can, but we're not actually teaching the skill. We're teaching people how to go onto a new build site and get a building that looks okay to sell. So a lot of that knowledge has been lost, unfortunately. And I work for a company that's people could argue we're guilty of it. We manufacture premix materials because it's just the way the industry has gone. Really, it's trying to make the best of a bad situation, I think. But lime isn't any more difficult to apply than gypsum, sand, and cement. And I think that's also potentially an issue. I do lots of contractors that I'm very friendly with. They almost do try and make it out to be much harder than it is to charge a little bit extra. If I'm being brutally honest.
Anything else to add, panel?
I think that is one of the advantages, isn't it, of the the ready mixes and the packaged products, and some people might turn their nose up at them and say they're not historic enough and they're not traditional enough, but they have been tested. They do have data sheets, so an architect can specify a product with that knowledge that he knows how it's going to perform because it's been tested that way. And I understand, Leap saying about the difficulty of specifying hot mixes, because it doesn't come with that data sheet. It's just really relying on someone on the ground doing the correct mix in the correct manner and ending up with results.
Just to add to what Graham has just said there, you don't have to do a hot mix on site where you get issues with health and safety, time spent mixing rather than applying. We can supply hot mixes, dry or wet, ready to roll. They are available in the market, so you don't have to mix your own.
I think also the industry's got slightly better at the language it uses. It was a very nostalgic and this sort of word traditional, which I'm not quite sure what that's about, because we are all still producing traditional materials because we're reacting to ethical, environmental influences which we have to try and improve the materials that we're producing. But I think the industry has been quite bad at looking back and not delivering the information in a slightly more scientific way, as Adam was doing with describing how these materials actually function, their physical characteristics and how they help the building. So I think that over the last sort of 20 or 30 years, that has slightly improved, but we're still, yes, in a slightly backward industry.
Dominic?
Yeah, I think I would just briefly like to endorse, obviously, what the other speakers have already said in terms of the education void. But we're all and have been for many years, and will continue to do, providing training to interested parties within the trades, and this is, it's a very important element of the whole mix. Pardon the pun. So where, Adam is completely right, saying, well, unfortunately, there's a lot of cases where people just prefer to stick with what they know, but the more ambitious among the trades, and we have quite a lot of experience, as I'm sure the other suppliers have, is it's finding those practitioners who are willing to learn something new. Even though, as Azam rightly says, it's actually no more difficult than the products they've used in the past. It's just takes a little bit more care and attention to detail, and they can achieve amazing results, as we're all evidencing in different examples, and wherever you go. Graham is in a part of the country where, as is the same for the southwest, there are just so many amazing buildings. They do need a lot of care and attention. They've been standing for hundreds of years because they were built with lime rather than cement. And so that in itself, is just lending itself to a whole opportunity for the industry. But there is quite often resistance, but I think we have to slowly but surely, over time, as we're all currently doing, break that down and bring more people into the sort of lime area, where they will be happy with what they can achieve. I mean, a lot of the materials that have been referenced today are extremely easy to use. It's like changing the sort of product you might use in a home. Go from one cleaning product to another product. They're all, there's not, at the end of the day, there's not such a huge difference. But in our case, lime is prescribed because of the nature of the buildings that we're endeavouring to maintain and show off for the long term.
Thank you, Dominic.
Thank you.
So we've got about 5 minutes left, and I appreciate we've covered quite a lot today. So perhaps if I could ask our panelists just to give sort of one key takeaway that you'd like people to leave with today that would make them feel sort of more confident about using Lime products in their projects, essentially.
I'd just say that we're here to give a helping hand. If you're not sure, drop an email or pick up the phone. It's what we specialize in. Yeah, always happy to help with specifications and suggestions.
And I'd just like to add, I think that we need to encourage people to look at cause and effect. We're very often looking at the effect and treating that rather than actually looking at the cause. And materials get a pretty bad press because we're blaming them. Where's the actual problem happening?
Thanks, Nigel. Adam, Graham, Dominic?
Yeah, I mean, for people wanting to give it a go, just give it a go. It's not. It doesn't need to be scary. There's no sort of magic, black magic type involved. It's doable. I think the one key takeaway is that from our perspective, or my perspective, there isn't a one size fits all. And as we've all echoed, it does unfortunately come down to very specific application within each building. But yeah, there shouldn't be this drive to say that we should only use material X or material Y or Z. All of these materials have their place. It's just spending a bit of time to try and understand, how they can best work for that application.
Yeah, I agree. I think that sort of covered all of the points, really. I think don't be daunted. Don't be daunted, rather, is the answer. I think it's very easy to get from a newcomer's point of view, very easy to go online, have a look at forums and get inundated with different opinions and arguments and squabbling. I think it's very important not to get involved with that. I think you're absolutely right. Ask someone that's in the industry and has some experience, but ultimately, I think don't spend all your time wondering about which product is right. I think we are absolutely correct. I think there are a multitude of products, but not one of them is going to do everything. And it's a case of making the best choice with the information you've got. But yes, I would say ask and then give it a go.
Dominic?
Yeah, I would endorse all of that. I think it's horses for courses. And there is quite a wide choice of product solutions. And yes, talk to us, email us. Any inquiries will be dealt with efficiently. And we're here to help people meet those challenges and end up with what they're looking to have at the end of the process. Thank you.
Excellent, thank you.
Echoing what Graham said, and it's generally the first a bit of advice when people come on courses is don't engage with social media. Yeah. It's the most horrific, toxic, critical, and I cannot understand how people have got so much time to be really rude.
Good question.
Yeah, couldn't agree more. It's one of the worst places to ever look if you're about to start a project.
Okay, well, stay off social media, but come to our next event. If you're interested in Lime and want to discuss more and sort of get into the detail, then we've got one of our material mornings sessions. So this is slightly more informal format where you can bring sort of specific project issues that you're facing, and we'll try and help you overcome them as best we can. So that's on the 7th of May. I've put the link in the chat. And Larry has put a link to the feedback form. So please let us know your feedback from today's event. It's really useful for shaping our future events. And we're doing well on time. So I think I'll say a huge thank you to Adam and all of our panelists for presenting. Hopefully you found that a really interesting session. I think we'll share the recording for this rather than the slides, because I think having that sort of annotation helps, Adam talking it all through. So we'll share that with you shortly. And hopefully see you at our next event. Good. Thank you.
Good to meet you all, and thank you. Bye-bye.